Good morning. Welcome to this session, Chapter 4, Semantic Analysis. We are now in the middle stage of the compiler design. Overview of semantic analysis in compilation flow. Before we conclude the front-end compiler, let's look at the compiler structure. The so-called front-end compiler, including the scanner, you have a source program, you create a lot of tokens. So basically how to do this, it's not too hard. Basically, if you have a Python program, you can actually read in data in a file, and then basically you just need to do some split for a certain file, such as a line you read in or something. Or the line you can actually do a strip to get rid of the /n or something, and then you do split. So that part is actually not too hard. And the split would split into token. And whether the token following the regular expression or not, you can have a different, you have actually work on using your own regular expression to detect that. Or the whole line you can fit into the regular expression before you do split. Okay, that's technically that's not hard. And then second one, we do parsing. Parsing we use based on the token, you do parsing and then get a certain result. After that, we need to do this semantic analysis, and we actually need to generate some simple table handler. And then we create this syntax tree. Okay, we attack this analytical syntax tree. And then we actually go into backend. The backend will be generating the machine code. So you need to select the instruction and then allocate a register. Sometimes not all variables are put into the memory, so you can put into registers. And then we generate the assembly language and then finish the program. And whether the assembly language need to further go into the machine code, it will depend on the compiler's option. Okay, so this is a compiler structure. And the example I'm giving here actually is the very famous GCC. This GNU compiler collection. Or you may see this G++ before, if you use the compiler before. And throughout this chapter, we are based on this compiler. So typical front end you will have is a source program, use the scanner to generate the token, and then you have a parser to pass them into syntax tree. And then it may have an error handler and the parser, and then you use this semantic analyzer. So in this section, we are mainly on this error handler and semantic analyzer. And after that, you may generate a simple table. And this simple table actually, as we mentioned before, it actually is a table that's being used for the whole process of a compiler. So the whole stage of compiler will use the simple table. And then you will have the instruction selector and the register selection allocation in here, and then go into backend. And the backend take the simple table and register and optimize it, and then generate. And then this one is independent, machine independent instruction generation and register allocation. And this one's dependent, machine dependent. So here may be a intermediate code, and here is the final code for the native code for the machine. So you have the register allocation, instruction scheduler, and the p-hole optimizer. And p-hole is when you have some instruction generated. I'm sorry. P-hole is when you generate some code, they might be a few clock cycle, and then there will be someone waiting for some resource to finish, and then you may have instruction in unrelated to this execution flow be put into here to steal some clock cycle, and then optimize for the compiler performance, CPU performance. That's called pit hole optimization. And then we generate the assembly code, and then finally assembly code go to the machine code. So this is the GNU compiler collection compiler. So you have the C language or C++ language. We pass through a compiler, and then actually your source code go into this GCC, and then we have assembler to assemble it, and then linker and static libraries, and then you get a target program, and some of the dynamic link library will be due at the runtime. So at compiler stage, we have something like this. So GCC is a collection that invoke compiler, assembler, and linker, and is not used for only C language or C++ language. So don't get confused, like this is a GNU C, C++ compiler. It's called GNU compiler collection. So GCC compiler architecture, you have input language, you have target machine, and then input language would feed into language specific code, and then pass that into actually with the parser. So here actually it was the input language. So maybe this is C language or C++ language, and then you have using the kind of the grammar like regular expression of content-free grammar, and then you use that to generate a parser to feed into a certain parser, and then your source program also being fed into the parser, and then you do the front end passing, scanning, passing here, and then send into gigafier. Gigafier will actually generate some intermediate code. Later we will show you what is the gigafier, and then there's the machine language machine independent generic code standard, and then you generate a tree single assignment optimizer, and then you go into expander, something like that, and then you start to move to the machine dependent code generation, and then recognition, and then your target machine provides a spec and participate in the later stage, and then eventually it generate your assembler. So it is way more complicated than the simple 6-stage description. So the GNU compiler collection is a compiler system produced by GNU project supporting various programming language. GCC is the key component of the GNU toolchain and the standard compiler for most Unix-like operation system. But actually, GCC is also available for personal computer. And GCC has played an important role in the growth of free software. So basically, if you know about GCC well, you will be we will be able to handle a lot of language, and also being able to become a professional programmer. So it was intended to compile C++ in December of that year in 1987, and then now developed for front end for Objective-C, C++, Fortran, Java, Ada, Go, and different languages. And version 4.5 of the Open MP message passing specification is now supported in C and C++ compiler. So later, he also supported the GNU C++ 11, C++ 14, and now C++ 17. So GCC is a compiler you definitely need to learn, and it will help you in your career development. And here, more specifically, we talk about C++ language and ARM processor or x86 machine. So machine-dependent part, you have the black boxes, and then this is language-dependent part. You have the orange one, and then green one is for language machine-independent part to do optimization. So the data flow view of the compiler, you may have different language, and all of those language generate a different abstract syntax tree, AST, and then those are just tree structure, and those tree structure being fed into the generic stage. So basically right here, you kind of accepting different AST, and right here, you have a generic stage, and then you will put into Gimbal program. So Gimbal program is a much more restrictive representation of AST. So basically, Gimbal is also a AST, but it actually is a decorated stage. So here, Gimbal actually is the semantic analysis we will see today in more academic term. We call it semantic analysis, but here in GCC is called Gimbal stage. And Gimbal stage actually is the 3 edges of representation derived from generics by breaking down the generic expression into tuples of no more than 3 operands. So later you will see the generic and a Gimbal format, and they are based on the AST generation. And then after that, we assign to the single assignment stage is a static single assignment form, and that static single assignment form is an expansion of the Gimbal instructions, and then it will go into maybe more than 20 or more process optimization stage, and then on single assignment, assemble them back, and then put into register transfer row level language. It's called register transfer language, and then go back to machine code. So, but this RTL is actually at this stage, you see Object-C, C++, Java, Fortran 77, all with AST representation. At this stage, everybody are at the register transfer level. Then we can compile and link together to the assembly code. So all these language can be actually shared and call each other. So here are those languages supported. Important passes. We have a source program, we pass it, generate a abstract syntax tree. There's a format called 003t.original, and then we pass into Gimbal files, generate the Gimbal format, and then we pass through the control flow grammar. Okay, here it is a different. This is called CFG. It's not content-free grammar. It's control flow graph. But these two actually, I would say, its meaning is called CFG, but the two actually are very close. I will explain the difference. But here is actually control flow grammar, not content-free grammar. Okay, I'm sorry, control flow graph is not content-free grammar. Okay, so here be careful. It's CFG. And then we go into the RTL generation. That's register transfer level language, and then register allocation, prologue, pro or epilogue generation, pattern matching, and to the assembly code generation. So here are those intermediate format. Okay, so it's not as simple as the 6-stage compiler that only has 6 stages. Here you have maybe more than 20 different representations in the GCC process, but we will see example right here about what they are. So here, first, if you compile GCC, you put -f, dump -tree -original -row for test.c. You will see your program done with this, and as you can see right here, it actually contains a few. It's just like you have some simple table. You have a blind expression, so this look like it's an terminal or non-terminal term. And over there is tell you the type, body, so it actually more like a decorated tree type. If you finish the AST dump, you have the different type assignment. So later when we go into the semantic analysis, you will see the decorated tree, but the decorated tree actually is more or less a file like this. It's not really a tree as you see the graphical view. It's actually dumped into such a condition. And then each of them has the tree structure as the link shown. Okay. But that tree dump is like this. After the tree dump, we kind of traverse through the tree and then actually convert it into the gimbal format. And the gimbal format is could be a file called list for the test.c program. And then as you can see, they are temporary or a variable being generated. That is original C code. And then here is the temporary assignment of several variables. And why we generate from here to here, this part is more machine related, and the previous one is our source program. And it's like almost like it can be converted into our instruction right away. But we still want to do optimization. So I'm sorry. And this one actually, if you do GCC, you can do -f dump tree -gimbal, and the previous stage is dump tree -original -row. So after gimbal file, you have this, and then we are going to generate a control flow graph. So before that, actually, we will introduce this idea of abstract semantic graph. In computer science, the abstract semantic graph or term graph is a form of abstract syntax in which an expression of a formal or programming language is represented by a graph whose vertices are the expression's subterm. So basically you have, let me see here, this tree actually means the parse tree we have. So you have like expression, but you actually end up with A plus B. So the thing it says like what the syntax tree is a programming language expression whose vertices are the subterms, but actually it can be further extended, okay? And they are decorated. So actually you decorate it with type, with value, with different thing over here. Later we will see in our lecture how to decorate that. So here this is ASG, and you basically have the syntax tree, and then you try to find the identification, type checking, and then values checking, generate an error message, and you have this decorated abstract syntax tree. So the term for decorated syntax tree and the ASG are the same. These two terms are exactly one term. So SSA decorated the ASG, and ambiguous parse tree. These different terms are actually meaning the same, similar stuff, except that they may have more subtle definition and more purpose, and it may be in a different stage for the optimization stage. And some maybe you don't want to optimize that far, so you actually sometimes there is a compilation flag. You can turn up this and turn down something, and something like that. And then our gimbal, it look like this. We have A equals 3, B equals 9. And all this ABC can be a temporary register or temporary variable. and C equal A plus B, something like this. And here we actually expand to static single assignment. So by doing that, we maintain the logical relationship. So A1 being used, and the next time we no longer use A, we will use A2 or A3 or A4. So that's single assignment. So we all assign to here, then we start to use B for B2 plus A3. So this actually is, you can consider 1, 2, 3, 4 like more like a timestamp or something. So we can actually have different variable over there, and there is the data dependency, but we can actually use that to actually expand that and do some optimization. So every variable is assigned only once. It's not like a programming language we are using. We have an A, and then the whole program has the same A. So every variable is only assigned only once, and then can be used for read-only value multiple times. So right-hand side, your A1 can happen several times, but left-hand side, you can only assign once. And then in if statement, merging take place, and we generate something called phi function. And then GCC perform over 20 optimization over SSA tree. So we have we got it from decorated AST, and now we into SSA, and over SSA tree, we actually will perform 20 more optimization. So those optimization will be done, and we do on SSA, and then we go to register transfer level language. So we get the tree from generic to Gimbal format to SSA transformation optimization process on SSA transformation, and then go back to register transfer level language, and then that will be suitable for backend assembly generation. Right here is the CFG control flow graph. We have this after the gimbal stage. We go through, we generate some temporary flow graph like this. And then suddenly this one is the decorated tree like this. And it is called graph, but it's actually a tree type. The reason why it's called graph is because there are certain paths it will feed back to certain stage. So the basic structure still be tree, but they will have some like this merging part and some feedback part. So we call it graph. But this guy is called control flow graph. It is similar to CF, the same show name as a CFG, like a context-free grammar, but it actually means different things. But if you think about it as context-free grammar, it's also fine because it's the end result after you use your context-free grammar to generate a control graph. So this one is like logically the last end result for context-free grammar. And after that, we use that. This one actually is past Gimbal already. So Gimbal will generate this context-free grammar and then go to control flow graph, and it actually is the end result for context-free grammar parsing. And then after that, we go into the SSA, and SSA is expanding this, and it actually is no longer related to any grammar content. It's actually more related to how we allocate the register and temporary variable to optimize the compiler performance. So beyond this, actually is called intermediate code generation. So context-free I'm sorry, I made the same mistake. This one is your control flow graph to SSA, and then we will go into from that. As you can see, the tree structure is the same, but actually it's just like from Gimbal, you have the assignment for the register, but here we have a single static single assignment for each register name. And then some of them you have a 5 function to help you to do optimization. And as for the 5 function, I think you can find some document to for description for 5 function. And 5 function is used when you do SSA assignment and un-SSA assignment. It would depend on the 5 function. It is actually a goal function for you to do optimization. It's just like a goal function. You want to optimize on the 5 function. And this is actually a evaluation tree. Okay. And let's continue. So CFG dump. So for example, I have a simple if A less than 12, A equals A plus B plus C, then we have this GCC-F dump -tree CFG list, you will get something like this. So not too terrible. You know, this one is actually the one we see over here. I'm sorry. It would be the CFG would be this one. The if 12 part. Okay. Okay. Okay, now let's go back to this one. So right here, if you see this one, it's actually more like if you really look at this this one is more like an assembly code jump less than equal, right? You have the 12, maybe R1 or R2. R1 is A, R2 maybe it is 12. Okay. And then else do something. This is more like the assembly code, right? It's more like assembly code doing assignments. So it's very ready to go into the assembly code. And then we, after the on SSA, you will go into this called RTL dump format. And there is a settings on register processes. So if you look at here, it's very more like something like Lisp code. It's like a little bit like Lisp. And actually it's like as a car Lisp language, you have the CAR, CDR, getting the first term, getting the rest of the terms, those operations. It's more like the Lisp language, the LISP Lisp language format. But it's actually related to the register transfer law language. After that, you actually go into this one is a assembly dump from this format. We further will go to assembly code. So final assembly code is like somewhat like this. So as you can see, we have the move over here. We have some pop. So actually it's only such simple statement. We get such, and some of them are not actually assembly code. It's like some description. And the real assembly code is these move statements and push statements. Okay, so that actually you do this and then you will dump out to A.out. A.out is the executable file. So right here you will get the assembly code. You'll be getting the test.s. That's the result for here. And then you can actually go further to generate the executable A.out file. So that's we actually show you the whole process for a typical compiler front end. So now we are going to start the semantic, the idea, talking about this semantic analysis. So the role for semantic analysis, following parsing, the next two phases are the typical compiler are the semantic analysis and the intermediate code generation. The principal job of the semantic analyzer is to enforce the static semantic rules. But we have the static semantic rule and the dynamic semantic rules. But here we only talk about static part. That means that those rules can be enforced by compiler. And construct syntax tree usually first the gimbal, CFG, SSA. Information gathered is needed by the code generation, SSA, IR plus, instruction selection, and register allocation. So that's the role of the semantic analysis. Basically, construct a decorated tree and then get those information needed for code generation for the next back-end stages. Role of the semantics analysis. There is a considerable variety in the contents to which parsing, semantic analysis, and intermediate code generation are interleaved. So even these three compiler stages may be interleaved. So each compiler have different processes. That's why in the beginning we showed you this GCC format, and that is more a commercial, not commercial one. It's actually a open source one, but it's actually a practical one, realistic example. A common approach interleave construction of a syntax tree with parsing, and then followed by separate sequential phases. So the parsing actually is up to the gimbal. And after the gimbal, actually you have those for optimizing, allocating register stuff. That's no longer related to parser. The role of semantic analysis. Semantic rules are further divided into static and dynamic semantic, as we mentioned. Static is compiler dependent and dynamic is runtime. So the compiler enforces static semantic rules at the compile time. It generates code to enforce dynamic semantic rule at runtime. So this one is unchecked, but they generate a rule. Type checking and report errors at the semantics analysis stage. That's another job for semantic rule. So basically, generate a rule, enforce the rule, and then check the errors. And then both semantic analysis and intermediate code generation can be described in terms of annotation. And the annotation, we call it the declaration of parse tree, and the end result will be decorated decorated abstract syntax tree. And then this abstract decorated syntax tree is called based on the attribute grammar that we will be talking for this in this chapter, and that grammar is for decoration. And the end result of decorated abstract syntax tree will be in the gimbal format in GCC compiler. Attribute grammars provide formal framework for decoration of a tree. Topic in this chapter, we have attribute grammar framework, which is a useful conceptual tool even in compilers that does not build a parse tree or syntax tree as the explicit data structure. And we have attribute flow that is used to evaluate the abstract grammar that constrains the orders in which nodes of a tree can be decorated. Most compilers require decoration of the parse tree to occur in the process of an LL or LR parser. So we have attribute grammar, attribute flow for the execution flow, and we have action routine that is used as a ad hoc mechanism for such on-the-fly evaluation. So we evaluate the partial result and put back to some attribute in the attribute grammar, and then manage of the space for the parse tree, and then tree grammar and the decorated syntax tree generation. So here are the topics for this semantic analysis. Basically, you need to have the attribute grammar. That is the add-on grammar beyond the context-free grammar. You have this one to declare a tree. And then after you declare a tree, you evaluate the tree based on the declaration of your tree. And then we actually add those action routines so we can basically be able to evaluate the tree. And also we can also find out what are the errors based on these three different things. Static versus dynamic semantics. What are the static semantics? It's attribute grammar, and then dynamic semantics does not cover in this chapter, but they are operational semantic and axiomatic semantic and denotational semantics. So here we have a comparison between static and dynamic semantics. We use the term static to describe the property that a compiler can determine without any particular execution. So without running the program, if we can find the semantic analysis, we call it that actually is the static semantics. So right here we define a function that is for Python, and both x refer to the same variable. Dynamic property are those depend on particular execution. So something like this, if you actually have an exception depend on the runtime, that is a dynamic property. So it actually more like operational semantics, whether we have divided by 0 or not. Without run it, we don't find out it. So actually a decision now is not really that simple. So for example, we have this. The compiler can deduce that x and y are integers. For example, if you are in Python case. Both languages are often designed to require that we treat the variable only according to explicitly declared type, but deduction are difficult and impossible in general. So these are the difference between attribute grammar and these three different grammar for static and dynamic semantics. Dynamic checks. Many compilers that generate code for dynamic checking. So even though we do not have the possibility to prevent or figure out the error for the runtime, but we certainly are able to generate code to check whether there is a runtime problem or not. So we can provide code dump, we can provide exception. So it's customary in some organization to enable dynamic check during program development and test, and then disable them for production. So commercial tools do have such capability to do dynamic check for the program at the development or debugging time. And errors may be less likely in production. So in production, we don't want the code dump or something like that. We may allow the program to run with bugs. Usually not all bugs are fixed, and some of the rarely encountered bug actually will be allowed for production usually. And for example, like Microsoft Office may have about 100 bugs that you never know, but you do run into that trouble. So sometimes the software will freeze, sometimes the software may break for some reason, but because it's so rare, sometimes the bug will be allowed to exist. And so, but we don't want to have the compiler to complain. So the runtime you have a code dump. On modern processors, it is often possible for dynamic checks to execute in pipeline slots. Pipeline slots is a pipeline slot is like the execution flow for each instruction. You have some instruction, we call it is the pipeline slot, and these instructions are run in the pipelined format. 4 or 5 stages of the instruction. So each one of these, we call it a pipeline slot. That would otherwise go unused. So dynamic checking actually will optimize the tree, making them virtually free. On the other hand, some dynamic checks are sufficiently expensive that they rarely implement. Okay, some checking is so expensive, take too much time, but you really don't want the compiler to be that slow, so they may not be used. Assertion in Java. An assertion in Java is a statement that a specific condition is expected to be true when execution reaches a certain point in the code. Assertions were added in Java 1.4. They were used to verify the correctness of an invariant in the code. They should never be triggered in the production code. So basically, it will hold a program. If the assertion is true, it will pass, but if it is wrong, an error will be raised. But this assertion for debugging is already been removed or been almost obsolete because it was replaced by the exception handling routine. And we actually have a JUnit to do testing, so there's no longer required to put those assertion. And assertion right now actually is a bad idea. So for programmers should learn how to use the unit testing and exception handling mechanism instead of using the assertion. But these two different testing techniques are actually used to replace the assertion. So assertion is a way to provide the holding of your program at the runtime, but now it's replaced by unit testing instructions and exception handling routines. Assertion in C++. Many languages support assertion via standard library. So in C++, we can assert this denominator not equal 0 for the divided by 0 assertion, but when it error occur, we will see this. The C manual requires assert to be implemented as a macro or built into compiler so that it has access to the textual representation of its arguments. So this is required for C++ for every implementation. And assertion, of course, could be used to cover the other three sort of check, but not as clearly and succinctly. And actually, same thing for assertion in C++. Now we have the exception routine. So assertion was replaced as well. Some languages like included and LFL implementation allow the programmer to disable assertion. I think that's a better idea. And the related construct were when desired to eliminate their runtime cost. So basically, nowadays assertion is not popular. Exception handling is more popular. Static analysis. In general, compile time algorithms that predict runtime behavior are known as static analysis. Type checking, alias analysis, escape analysis, subtype analysis, and optimization. These are different static analysis. So let's look at the type checking. Most static but dynamic loaded classes and typecast may require a runtime check. Okay, so array, subscript, variant, record, text, and dangling pointers. Alias analysis determines when value can be safely cached. Escape analysis determines when all references to a value will be confined to a given context. Subtype analysis determines a variable in OOP, object-oriented programming, to have certain subtypes. Optimization, unsafe, lead to incorrect code. Speculation, to improve performance but degrade sometimes. Here are 4 different levels of optimization. Some are unsafe, some are speculative, some are conservative, some are optimistic. So these are different levels of things. So unsafe will leave incorrect code. Improve performance but degrade sometimes. Guarantee that it is safe and effective. And this one, optimize, is literal use of speculative optimization. So here is all different level of optimization for the static checking. So you need to determine which level you will implement. Attribute grammar number 1. So attribute grammar, what is actually is attribute grammar? Both semantic analysis and intermediate code generation can be described in terms of annotation. So it's add-on feature to the context-free grammar. So actually it's a add-on feature, is annotation and declaration of a path tree. So we got a tree, but now we want to add something on it. And the way to add things to it is called attribute grammar. What kind of attribute will be generated for the certain node? So sometimes it's a value, sometimes it's a sum, sometimes it's a check condition flag or something. So attribute grammar provides a formal framework for decorating a tree. The note below discuss the attribute grammars and their ad hoc cousins, action routine. So action grammar is some decorated term, and there is another thing called action routine for you to do something about it, reporting error or something that you want to do after you check the grammar. Attribute grammar, we will start with declaration of path tree, then consider syntax tree. Path tree is the tree we generated. Syntax tree is more detailed syntax and with declaration. Consider the following LR button-up grammar for arithmetic expressions made of constants with precedence and associativity. Now we are going to look at this LR grammar. Attribute grammar, the attribute grammar serves to define the semantics of the input program. Attribute rules are best sort of a definition, not assignment, so it's a definition. They are not necessarily meant to be evaluated at a particular time or in any particular order, though they do define their left hand in terms of the right hand side. So basically, attribute grammar also will derive data so that the right hand side will feed the result back to the left hand side. And it's actually a evaluation tree. So later when we look at the real example, we will know this better. Now let's look at this arithmetic grammar. We have expression that defines expression and term. Expression equals expression minus term. Expression can be a term. So expression has 3 things. Expression can be an expression plus term minus term, or be the term itself. And the term can be a term times factor, or can divided by factor, or it will be factor itself. So term can be a factor times factor times factor, or factor divided by factor divided by factor. So these 2 grammar actually show you a way to write a good grammar, and simple way of writing a good grammar. It's like we have something called term, and this guy term actually is A times B times C. So turn can be a turn times factor. And each of these is actually a factor. So, and turn can be a turn divided by factor. And then turn can be a factor. So in fact, turn is built upon factor. And this grammar tells you that. And this one is similar. We have this guy, A plus B minus C minus D. So this one, the whole thing here can be an expression minus T, and this T actually is a factor as well, and then this is the D, right? And this expression can be an expression minus a term, and this term is C. And this term can be an expression plus T, and this T is actually B, and this term expression plus term, and term can be A. This is B, I'm sorry. Okay, so as you can see, this is a simple grammar for arithmetic, and factor can be its own negation or a parenthesis, or it can be a constant. So this down to the lower term. So three of each rule, it actually is definition for expression, term, and factors. So that's not how to understand that. So the grammar will generate properly form the constant expression over the basic arithmetic operators, and it says nothing about their meaning. To tie the expression with mathematical concept, we need additional notation. So here we have this content-free grammar, and it's undecorated. We can generate a tree that I just wrote, but we now need to actually add the attribute. In our expression grammar, we can associate value with each expression, and a term and factor and constant in grammar. So we can have the s star value for the form s. Because soon the value of a constant provided by our scanner, we must invent a set of rules for each production. So let's look at that. So the previous content-free grammar will be decorated with this value. So E1's value equals sum of E2 and T val. So T's value, as defined here, can be a product of this T2 times the F value, or is a quotient of this. So as you can see here, you actually have a function of the right-hand side assigned to the value of the left-hand side. And you actually build up the semantics for the parse tree. And this is called attribute grammar. So this one actually gives you a better idea of what is the attribute grammar. So attribute grammar, a redux version. In the strict definition of attribute grammar, copy rules and semantic function calls are the only two kinds of permissible rules. In our example, we use this right pointing triangle symbol to introduce each code fragment corresponding to a single rule. In practice, it is common to allow rules to consist of small fragments of code in some well-defined notation, so that the simple semantic function can be written inline. So it's something like this. It's like this E value equals E2 and t dot value maybe plus minus or something. And we can actually write down this as this. So that is a seventh way of doing it. Attribute grammar. The purpose of attribute grammar is to associate meaning with the grammar. We can use any annotation and the types whose meaning are already well defined. In example 4.5, we associate numerical value of a symbol in the context-free grammar and thus with parse-tree node. And then using semantic function shown ordinary arithmetic. So it's actually showing it by the example. It's actually talking about this one. It's talking about this one. We use the arithmetic function to associate with the nodes. Okay, so in the compiler interpreter for a full programming language, the attributes of a tree nodes might include, and for an identifier, a reference to information about it in a simple table. For an expression, its type. For statement, expression, and reference to corresponding node codes in the compiler's intermediate form. For almost construct, indication of the file name, line, and the column where the corresponding source code begins. For an internal node, a list of semantic errors found in the subtree. So basically, what this actually say is that here are so many different attributes, and those attributes will be added to the tree as an attribute grammar, and then it will do something. So basically, a reference for information about a simple table. You actually build up a tree. You build up a tree, expression, turn, and then times, and then factor something, and then there's a reference. Okay, factor, go to the table, entry, how many is the ID, and then A or B or something, and then give you the type. So this guy is an integer. Okay, and then there's an indicator that the file line number, okay, line 15 for that A variable, something like that. These are the different information that you put into the attribute grammar for your evaluation tree, syntax tree. So that's the attribute grammar. So they are values, they are reference to the table, they are construct indication, they are error reporting stuff. That's all included in the attribute grammars. Attribute grammar number 2. Attribute grammar is a special form of context-free grammar where some additional information are appended to one or more of its non-terminal in order to provide context-sensitive information. Each attribute has well-defined domain of value, such as integer, float, character, string, or expression. Attribute grammar is a medium to provide semantics to the context-free grammar, and it helps specify the syntax and semantics of a programming language. Attribute grammar can pass values or information among the nodes of a tree. Example, this is a attribute grammar term. The right-hand part of the context-free grammar contains the semantic rules that specify how the grammar should be interpreted. Here, the value of non-terminal ent are added together, and the result is copied to the non-terminal e. Semantic attribute may be assigned to their value from their domain at the time of passing and evaluate at the time of assignment or conditions. Based on the way the attributes they get their value, they can be broadly divided into two categories: synthesized attribute and inherited attribute. So here we introduce a concept. There are two types of main attribute, the synthesized and the inherited. So other than that, as long as we understand the content-free grammar, it's not that hard. So attribute grammar carries some semantic information along through parse tree. Use for semantic, static semantic specification, static semantic checking in compilers, and attribute grammar is a content-free grammar with annotation. So here is something important. It's a content-free grammar with annotation, and those annotation with attribute value and a set of predicates for checking the attribute consistency. So content-free grammar with the 5 types of information that we described, that is an attribute grammar. What are the 5 types of grammars? Let me see. No, not here. The one we just mentioned. Not in here. Yeah, this is the 5 type of the information that we will obtain for the attribute grammar that we just mentioned. So this actually show you the attribute grammar is a content-free grammar, and with that 5 type of declarations, and then you can actually do something more. So attribute grammar has 2 types of attribute. One is synthesized attribute, one is inherited attribute. Here are the mathematical definition. Synthesized attributes are determined from the node of the child parse tree. If x derived by x1, x2 to xn is a rule, then the attribute s of that function of that non-terminal equals the function of the right-hand side. The value of x is not determined by the children. Parse semantic tree information of the tree. So to be short, I give you a simple example. It's like this expression equals a expression plus term. So the value of this expression equals the value of expression plus value of the term. This is actually what this is. The value is s. This is sum. So here, let me see. It's a sum of the. I'm sorry. It actually is sum of value of e plus and the value of t. That is this function. So this is called a synthesized attribute. And the inherited attribute is different. Inherited attributes are determined from the parent and siblings, especially the elder siblings. And it's something like this. It's a sibling to the left of the tree, parse semantic information of the tree. Usually it's like I have a string S equals A plus B plus C. This may be something like integer, it may be float. This one maybe is string type. On the left hand side, string type. So the attribute of a certain guy on the right is integer type, but eventually the attribute will depend on the left hand side, the elder brother and the parents. Elder brother and parents will determine the inherited attribute. synthesize attribute. These attribute get value from the attribute value of their child, just like the S equals A plus B plus C. So S taking value from the child node ABC, and we use that example. Okay. Inherited attribute, in contrast to the synthesized attribute, inherited attribute can take value from parent or sibling, and usually the elder siblings. As the following production rule, like this: A get value from S and B and C, B can get value from S, A, and C, and likewise C can take the value from S, A, and B, but usually it's the left-hand side attribute. So expansion, when the non-terminal expand to terminals per grammatical rule, some days, the down way is called expansion, upturn is called reduction. If you get a value, move up, get a value, move up is reduction. If you try to evaluate deeper, it's actually expansion. Reduction, when the terminal is reduced to its corresponding non-terminal, according to the grammar rule, syntax trees are parsed top down and left to right. Whenever reduction occurs, we apply the corresponding semantic action or rules. So integer 5 equal value equal 5, type is integer, present value is 5. So these are the declaration. Semantic analysis uses semantic directed translation to perform above task. Semantic analyzer receives AST's abstract syntax tree from its previous stage. Semantic analyzer attach the attribute information with the tree. We call it attributed abstract syntax tree, but this is also called decorated or attributed or context or attribute grammar graph. There are several of them, all meaning the same thing. Attributes are two tuples, attribute and name. So here we have a type that's integer, and type depends on the left-hand side value. So this one says what it is, and the value is sum. So here is a syntax-directed translation scheme. We have these. We go through the tree, and we generate different value for that, and then the tree is look like this. It's a syntax-directed translation. The conceptual view of syntax-directed translation, we have input strings, parse tree, dependency graph, evaluate order for the semantic rules. The syntax-directed definition, this is a generalization of content-free grammars in which each grammar symbol has an associated set of attributes and rules. Attributes are associated with grammar symbols and the rules associated with the production. So what? So probably we actually, remembering the tree type, you will understand what's syntax-directed translation scheme. It's basically annotated the parse tree for this expression. S attribute SDT. So S type is a synthesized type attribute. So let's look at this. We have E equals E plus T, and then we will write down like this. As depicted above, the attribute in S attributed SDT are evaluated in bottom-up parsing, as the value of the parent node depends upon the value of the child nodes. L attributed SDT. L actually is the left-hand side, and it actually is the, this one's called what? Inherited attribute. So S attribute, SDT is for synthesized. L means the inherited. This form of SDT uses both synthesized or inherited attribute, with the restriction of not taking value from right sibling. So basically, it's more like synthesized, more like inherited. So L attribute SDT, non-terminal can get value from its parent, child, subtree, sibling nodes. So it actually including the S type, but mostly of this is because we wanted to have the inherited feature. So S take value from A, B, C. A can take value from S only. B can take value from S and A. C can take value from S, A, B. So basically, this rule we go into the including the S attribute and the L attribute, and and L attribute including the synthesize and inherit both in L attribute. Evaluating of attribute. Let's have about 10 minutes break. We will come back for this, and we have already spent 1 hour and 15 minutes. So let's have a 10 minutes break. I'll come back.